A power function is a special type of polynomial function. It's a monomial, one term, in the form a times x to the n power. And since it's a polynomial function, we know that n, that exponent, has to be a non-negative integer. So if you just want to note, power function, it's a monomial, mono meaning one term. And here's some examples: 5x, negative 3x squared, x to the 11th power. So we're going to expand our library of functions, those list of parent functions that we studied earlier in the course. We're going to expand our parent functions with even and odd power functions. Okay, so even power functions, as it suggests, they're in the form f of x equals x to the n power. So the a value is is 1. The coefficient is 1 in even and odd power functions. So if it's an even power function, that exponent n is an even integer. So some examples: x squared, x to the 4th, x to the 6th, etc. So it turns out, if we look on our calculator, if we graph x squared, x to the 4th, and x to the 6th, and I'm going to graph them on a standard viewing window here, zoom standard, option 6. There's x squared, there's x to the 4th, and there's x to the 6th. So you can see, as you go from squared to 4th to 6th, the graph is getting more vertical. It almost looks like the idea of a vertical stretch, like we talked about before with our transformations. So if we want to make a sketch, if you notice though, they're all the same shape. They're all parabolas. They're just relative to one another. As the exponent increases, they get narrower or more vertical on the outside. It also turns out they have the same 3 key points. If you remember from our x squared parent graph, 3 key points on it were negative 1, 1, 0, 0, and 1, 1. Well, if you plug in a negative 1 and square it, that's the same as taking negative 1 to the 4th or negative 1 to the 6th. And if you put in a 0 for x, if you square 0, it's the same as 0 to the 4th and 0 to the 6th. And if you put a 1 in for x, same thing. 1 squared is the same as 1 to the 4th, same as 1 to the 6th. So it turns out these 3 key points are the same. So I'll call these common points 0, 0, 1, 1, negative 1, 1. So no matter the exponent on the even power function, they're all going to be parabolic, and they're going to go through these 3 key points. So you can see symmetry with respect to the with respect to the y-axis. And we can see its domain, of course, negative infinity to infinity. And the range from 0 to infinity. So in here we're saying as the exponent increases, a larger n value means the graph is more vertical on the outside ends. So on way to the right and way to the left, they look the same. When x is less than negative 1 and greater than 1, the outside ends, they become more vertical. Now, if we look back at these graphs, if I change my viewing window now, and I zoom in near the origin. So to zoom in near the origin, I'm going to change my window to negative 1 to 1 for the x and the y. Now if I graph, first is x squared, then x to the 4th, and then x to the 6th. So we couldn't see it when we were zoomed out, but it turns out that as that exponent gets larger, the graph actually flattens out and gets closer to the x-axis. So as the exponent goes from squared to 4th to 6th, etc., as it gets larger, on the ends, on the outside ends, it's going to become more vertical, steeper, if you will. And then the graph is going to become flatter or closer to the x-axis if you zoom in near the origin between -1 and 1. Similarly, if we look at odd power functions, so we know an odd power function, same form, f of x equals x to the n, so you've got again that a value of 1, that coefficient is 1, and since it's a polynomial function, we know n is a non-negative integer, and in this case, n is an odd integer. So examples of odd power functions, x cubed, x to the 5th, x to the 7th, etc. So we're already familiar with an x cubed graph, so we know this is going to be that increasing shape, that snake shape. So if we go into our calculator now, and I change my exponents here, I'm going to change this to odd powers, so x cubed, x to the 5th, and x to the 7th. Now, remember, I'm still zoomed in close to the origin. So if I graph, I see a snake shape. There's another snake shape getting closer to the x-axis, and there's another snake shape getting even closer. So they're all the same shape, just like all the even power functions are parabolas, all the odd power functions are that same snake shape, and the same thing happens as you zoom in near the origin. It gets flatter or closer to the x-axis. So if I change my window now, if I zoom back out to a standard viewing window, there's x cubed, there's x to the 5th, and there's x to the 7th. So just like the even power functions become more vertical on the ends, it's the same for the odd power functions. So we can make a little sketch here of our snake shape that we already know. So it turns out all of the odd power functions have the same shape, and those same three key points, -1, -1, 0, 0, 1, 1. And again, because if you put a -1 in for x and cube it, you get the same thing as taking -1 to the 5th or -1 to the 7th, same with the 0 and the 1. So you have the same three key points, common points, 0, 0, 1, 1, -1, -1. So you've now expanded your library of functions, besides all those basic parent shapes that we learned earlier, the absolute value, the cube root, the square root, etc. Now you can expand that to even and odd power functions. So any odd power function is going to be this shape with these same three key points. Now we can see this symmetry is symmetry with respect to the origin. We can see the domain is -infinity to infinity, and the range as well, -infinity to infinity. And just like with the even power functions, as the exponent gets larger, as that n value increases from cubed to the 5th to the 7th, etc., it means the graph is going to become more vertical on the ends, on the outside, and then if you zoom in near the origin, it will become flatter. Oops. Flatter or closer to the x-axis.